Simultaneous equation models are a form of statistical model in the form of a set of linear simultaneous equations. They are often used in econometrics, structural and reduced form. Suppose there are m regression equations of the form where I is the equation number, and t equals 1. T is the observation index. In these equations xit is the key times one vector of exogenous variables, yit is the dependent variable, y minus I, t is the ni times one vector of all other endogenous variables which enter the ith equation on the right-hand side, and uit are the error terms. The minus I notation indicates that the vector y minus I, t may contain any of the y's except for yit. The regression coefficients beta I and gamma I are of dimensions key times 1 and ni times 1 correspondingly. Vertically stacking the t observations corresponding to the ith equation, we can write each equation in vector form as where yi and ui are t times 1 vectors, she is a t times key matrix of exogenous regresses, and y minus I is a t times ni matrix of endogenous regresses on the right-hand side of the ith equation. Finally, we can move all endogenous variables to the left-hand side and write the m equations jointly in vector form, as this representation is known as the structural form. In this equation y equals y1 y2, ym is the t times m matrix of dependent variables. Each of the matrices y minus I is in fact a ni-columned submatrix of this y. The m times m matrix gamma, which describes the relation between the dependent variables, has a complicated structure. It has ones on the diagonal, and all other elements of each column I are either the components of the vector minus gamma I or zeros, depending on which columns of y were included in the matrix y minus I. The T times K matrix X contains all exogenous regresses from all equations, but without repetitions. Thus, each she is a key-columned submatrix of X. Matrix beta has size K times M, and each of its columns consists of the components of vectors beta I and zeros, depending on which of the regresses from X were included or excluded from she. Finally, U equals U1 U2 is a T times M matrix of the error terms. Post-multiplying the structural equation by gamma minus 1, the system can be written in the reduced form, as this is already a simple general linear model, and it can be estimated, for example, by ordinary least squares. Unfortunately, the task of decomposing the estimated matrix into the individual factors beta and gamma minus 1 is quite complicated, and therefore the reduced form is more suitable for prediction but not inference. Assumptions. Firstly, the rank of the matrix X of exogenous regresses must be equal to K, both in finite samples and in the limit as t infinity. Matrix gamma is also assumed to be non-degenerate. Secondly, error terms are assumed to be serially independent and identically distributed. That is, if the tth row of matrix U is denoted by U, then the sequence of vectors U should be IID, with zero mean and some covariance matrix sigma. In particular, this implies that EU equals 0, and EUU equals T sigma. Lastly, the identification conditions require that the number of unknowns in this system of equations should not exceed the number of equations. More specifically, the order condition requires that for each equation K plus ni K, which can be phrased as the number of excluded exogenous variables is greater or equal to the number of included endogenous variables. The rank condition of identifiability is that rank equals ni, where pi I0 is a times ni matrix which is obtained from pi by crossing out those columns which correspond to the excluded endogenous variables, and those rows which correspond to the included exogenous variables. Estimation. 2 stages least squares. The simplest and the most common estimation method for the simultaneous equations model is the so-called 2-stage least squares method, developed independently by Thiel and Basman. It is an equation-by-equation technique. where the endogenous regresses on the right-hand side of each equation are being instrumented with the regresses x from all other equations. The method is called two-stage because it conducts estimation in two steps. Step 1. Regress y minus I on x and obtain the predicted values. Step 2. Estimate gamma I, beta I by the ordinary least squares regression of y on and xi. If the ITH equation in the model is written as where Z is 80 times matrix of both endogenous and exogenous regresses in the ITH equation, and delta I is n-dimensional vector of regression coefficients, then the 2SLS estimator of delta I will be given by where P equals x minus 1x is the projection matrix onto the linear space spanned by the exogenous regresses, x. Indirect least squares. Indirect least squares is an approach in econometrics where the coefficients in a simultaneous equations model are estimated from the reduced form model using ordinary least squares. For this, the structural system of equations is transformed into the reduced form first. Once the coefficients are estimated, the model is put back into the structural form. Limited information maximum likelihood. The limited information maximum likelihood method was suggested by Anderson and Rubin. It is used when one is interested in estimating a single structural equation at a time, say for observation I. The structural equations for the remaining endogenous variables y-1 are not specified, and they are given in their reduced form. Notation in this context is different than for the simple IV case. One has the endogenous variable, the exogenous variable, the instrument. The explicit formula for the LIML is where m equals I minus x minus 1x, and lambda is the smallest characteristic root of the matrix, where, in a similar way, m equals I minus xi minus 1 xi. In other words, lambda is the smallest solution of the generalized eigenvalue problem. See Thiel. K-class estimators. The LIML is a special case of the K-class estimators, with several estimators belong to this class. Kappa equals 0. Als. Kappa equals 1. 2SLS. Note indeed that in this case, the usual projection matrix of the 2SLS, kappa equals lambda, LIML, kappa equals lambda alpha. Fuller estimator. Here K represents the number of instruments, n the sample size, and alpha a positive constant to specify. A value of alpha equals 1 will yield an estimator that is approximately unbiased. Three-stage least squares. The three-stage least squares estimator was introduced by Zellner and Thiel. It combines two-stage least squares with seemingly unrelated regressions, using cross-equation restrictions to achieve identification. In simultaneous equations models, the most common method to achieve identification is by imposing within equation parameter restrictions. Yet, identification is also possible using cross-equation restrictions. To illustrate how cross-equation restrictions can be used for identification, consider the following example from Wooldridge. y1 equals gamma 12 y2 plus delta 11 z1 plus delta 12 z2 plus delta 13 z3 plus u1 y2 equals gamma 21 y1 plus delta 21 z1 plus delta 22 z2 plus u2, where z's are uncorrelated with u's and y's are endogenous variables. Without further restrictions, the first equation is not identified because there is no excluded exogenous variable. The second equation is just identified if delta 13 0, which is assumed to be true for the rest of discussion. Now we impose the cross-equation restriction of delta 12 equals delta 22. Since the second equation is identified, we can treat delta underscore 12 as known for the purpose of identification. Then, the first equation becomes y1 delta 12 z2 equals gamma 12 y2 plus delta 11 z1 plus delta 13 z3 plus u1. Then, we can use as instruments to estimate the coefficients in the above equation since there are one endogenous variable and one excluded exogenous variable on the right-hand side. Therefore, cross-equation restrictions in place of within-equation restrictions can achieve identification. Simultaneous equation models are a form of statistical model in the form of a set of linear simultaneous equations. They are often used in econometrics, structural and reduced form. Suppose there are m regression equations of the form where I is the equation number, and T times key matrix of exogenous regresses, and y minus I is a T times Ni matrix of endogenous regresses on the right-hand side of the ITH equation. Finally, we can move all endogenous variables to the left-hand side and write the m I and gamma I are of dimensions key times 1 and Ni times 1 correspondingly, vertically stacking the T observations corresponding to the ITH equation. We can write each equation in vector form as where y and ui are T times 1 vectors, she is 8 variables which enter the ITH equation on the right-hand side, and uit are the error terms. The minus I notation indicates that the vector y minus I t may contain any of the y's except for yit. The regression coefficients bt equals 1. T is the observation index. In these equations, xit is the key times 1 vector of exogenous variables, yit is the dependent variable, y minus I t is the Ni times 1 vector of all other endogenous variables.